All right. Hi, everyone. I'm Tom, and I'm going to be talking about more predicting of wildlife crossing use, similar to what Fraser did, but slightly different methods. So hopefully you won't get too bored. But anyway, we know that roads have diverse impacts on wildlife, ranging from direct mortality from vehicle collisions, fragmentation, to everything in between. And we also know that wildlife crossings help to reduce impacts of roads by providing animals with safe passages across those roads. Now, wildlife crossings are often built for a particular species or groups of species. For example, large migratory ungulates throughout North America, mountain lions in California, or ocelots in Texas. Yet a wide variety of species benefit from wildlife crossings, not just our target species. So it's important to consider how we actually assess the effectiveness of wildlife crossings. For our target species, especially those that are non-migratory, we may only expect an individual to use a wildlife crossing once every few years. For example, with ocelots in Texas, we get very few detections, and it maybe happens once in a 5-year monitoring program, which is a little unfortunate if we want to see if crossings work for ocelots. But typically, because crossing monitoring is done with camera traps, we might be able to use the species diversity at those wildlife crossings to help predict whether rare species will use those crossings. So we know that typically more diverse locations, more diverse sites have more rare species. So looking for increased diversity at a crossing might mean that this crossing is better for an ocelot, for example. Let's see if I can change slides. We also know that many factors influence wildlife crossings. As Fraser said, there are broad-scale landscape structure effects to really fine-scale vehicle noise and vehicle traffic. However, at more moderate spatial and temporal scales, the characteristics of the crossings themselves, including their size, the substrate, the surrounding vegetation, daily vehicle traffic, and human activity around that crossing, could be really important in determining whether animals actually show up at that crossing, and then once they show up, whether they actually pass through the crossing. So the objectives for our study were to, one, determine the relative contribution of structural, environmental, and anthropogenic characteristics on wildlife crossing use of the mammal community, and then develop a model of community crossing use to be able to predict diversity at new crossings to inform construction efforts of those crossings. Now, we took this community-based approach and modeled community composition and therefore beta diversity. Now, for this study, we examined total detections, successful crossings, and failed crossings. So how many animals were at the site versus how many animals actually passed through the site, through the crossing itself, or did not pass through the crossing itself. But for the sake of time for this talk, I'm only going to talk about total detections. I don't know why this isn't working. Anyway, our study area was South Texas, an area where wildlife crossings are being built for the endangered ocelot. So ocelots in Texas are only found in 2 subpopulations, and the greatest threat to ocelots is roads and associated vehicle collisions. Now, currently, 18 wildlife crossings have been built on 3 highways in and around the Laguna Atascosa National Wildlife Refuge in Cameron County, Texas, so very close to the border with Mexico, and it's home to about 20 or so individual ocelots. Now, the construction of these crossings occurred over several years, with crossings on each highway being completed at different times. We monitored all 18 of these wildlife crossings using camera traps from the time the crossing opened to animals until about 1 year after construction ended. We used between 2 and 12 camera traps at each of our sites. Depending on the size of the structure, we wanted to make sure that we fully captured everything that was using that wildlife crossing. And then once our photos were sorted, we determined how animals interacted with that crossing. We classified these into 4 different categories. A was a successful crossing. The animal went from one side to the other. A B, an animal entered the crossing but exited on the same side. C, the animal approached the crossing but didn't actually enter the crossing. And a D, the animal was seen in the area but never actually interacted with that crossing. For our total detection analyses, we just combined all 4 of these categories into a single category of detections at a wildlife crossing. Next, we measured several characteristics of each of our wildlife crossings and assigned them to structural, environmental, or anthropogenic. Our structural characteristics included the openness ratio, which is the height times the width divided by the length, the substrate, the presence of a catwalk, which is just a raised concrete step, which allows passage during flooding events, and then the length of the fencing. Our environmental characteristics included the percent natural cover around the crossing, percent water, and percent woody cover, as well as the total monthly precipitation. Woody cover was specifically included because it's been shown to be really important for not only ocelots, but a lot of different species in South Texas are found more often in areas with greater woody cover. Finally, our anthropogenic characteristics included the traffic volume and the traffic speed. Traffic volume was the average annual daily traffic. The speed was just the speed limit. We didn't have actual speed information or actual traffic levels. We also included the presence of buildings in the area, as well as the human activity, livestock activity, and domestic animal activity at the wildlife crossings. Now, to address our two objectives, we used variation partitioning and distance-based redundancy analysis, or DBRDA for short. So variation partitioning is a method that allows us to identify the relative contributions of different sets of predictors. So in this case, that's structural, environmental, and anthropogenic. So it makes it a really great tool to look at how these three characteristics impact overall crossing use. Now, DBRDA is a multivariate regression technique that allows us to examine how community composition is affected by our suite of predictors, these same structural, environmental, and anthropogenic predictors. Now, because it is regression, we can then use it for prediction purposes, and we can validate models in the same way you would validate a traditional regression model. In our analyses, because we had 18 wildlife crossings, we just dropped the whole site from the model, reran the model, and then tried to predict that site based on its structural characteristics to see how well it worked. So starting with our variation partitioning results, when we just look at our structural, environmental, and anthropogenic factors, they didn't really contribute that much to the overall variation in our models, under 3% each, which isn't a lot, but for multivariate models, that's actually like pretty significant, and all of them were contributing a statistically significant proportion to the variation. So if we removed them, then we would actually lose something in our predictability from that model. So it's important to keep all of them in there. We can also see here that our anthropogenic characteristics contributed the most to the variability in these models compared to structural and environmental characteristics. So some previous research has shown that structure is actually really important, especially early on in a crossing's lifetime. So our study was over only the first year after construction. And as the animals get used to the crossings, they are learning about all these novel structures and what they are and whether or not they're safe. And those structural characteristics are really important, but that sort of goes away after a few years. We're actually showing that maybe anthropogenic characteristics may be masking some of those learning behaviors related to the structural characteristics. So it's clear then that human activity is probably playing a significant role in determining crossing use, at least here in South Texas. Now, moving on to some of our modeling results. So before we get into some of these results, let me just explain these diagrams, because you're going to see a lot of these biplots. So our shapes, those are our roads. Our colors are our individual crossings. So to interpret our results, each point represents the community composition in one month at one wildlife crossing. So points that are closer together in space are more similar in terms of community composition than points that are farther apart. So if we look then at the blue colors, we can see that our blue circles are more similar to our blue triangles compared to our blue squares. Now, before we do, oh, I put it up there right now. Anyway, before we do any regression, let's go back. And we can just look at our raw PCO scores. You can see that things are pretty jumbled. And we don't really see many. We see maybe some patterns, but we don't see too much. But as I already showed you, when we start fitting our regression, we really start to see patterns start to emerge. For example, our blue circles are now isolated in that top right-hand quadrant, which kind of makes sense. This site is characterized by really high human activity, and therefore it has a unique community composition compared to all of our other sites. For example, and then alternatively, our blue and green triangles, those are represented, they have water for substrate, so they also have a very unique community composition compared to the other sites. And we can see that they've kind of isolated themselves in the top left-hand quadrant. Now, when we start to do our prediction, we can see that, while not perfect, our sites begin to line up pretty similarly to where they were in our original model. So we can see that the blue circles still in that top right-hand quadrant, our blue and green triangles still in that top left-hand quadrant, and the majority of our sites still in that bottom right-hand quadrant. Now, this means that we can then very likely reasonably predict the community composition of these sites. So when we add our species scores to these figures, so now they're just getting more and more complicated, sorry, we can start to see that we can maybe predict what species might actually use these sites. So based on the structural characteristics and based on what the communities are at these sites, our blue circle sites are dominated by opossums and feral hogs, whereas our blue and green triangle sites are dominated by raccoons, beavers, and nutria. So, and then when we look at our predicted values, we can see that when we put those species scores on there, we can see that generally things line up pretty well. So our blue circles are still predicting opossum and feral hog use, whereas our blue and green triangles are still predicting raccoon, nutria, and beavers. And we can see that the majority of our other sites have a lot more different species. They're a lot more diverse. They get a lot more use. And you can't really see it on here, but there is a little bit of ocelot right here in the middle. Now, this is really critical in the evaluation of our model, where we want to really give managers a tool where they can have a particular set of characteristics of a wildlife crossing that they're interested in, and then you can see what kind of species you might be expected to use that wildlife crossing. So being able to predict what species might use a future crossing has some really significant conservation and management implications. First, we're going to be able to design better structures that are more likely to work for our target species. And second, we can begin to provide a framework to design scientifically informed crossings that are going to be more effective and more functional for a wide variety of species. Now, all of this can allow managers to design and implement better crossings that are more effective for more species, promoting landscape connectivity and reducing impacts of roads on mammals. Normally that would be the end, but I do have one more thing. Future work, some of the work that I'm doing now in the postdoc is that we're starting to get better understanding of how people are using landscapes. So we have human mobility data or anonymized smartphone locations, which we can then effectively map how people are using roads, off-road areas in both space and time. So we have that at very fine spatial and temporal scales, just like you would a GPS collar on a mountain line, for example. And we can begin to use that to get a better understanding of how people are using roads, and therefore how people on the roads are impacting how wildlife are using our wildlife crossings. So that beginning to integrate some of that could be a really great way to begin to get at some of those fine scale human impacts on wildlife crossing use that's been really hard to get at with previous work with AADT or camera traps or something like that. We can get at human use at crossings and around crossings. That could be really interesting in determining crossing use. We're still really, this is very new for us. So if anybody has any ideas or things that they want to look at with this cell phone data, always happy to talk. My email is right here. There is no I in my last name in my email, even though there is an I in my last name. Shit is a swear word, and previously Google wouldn't allow you to put swear words in email addresses. So that's what it is. Anyway, I'd like to acknowledge our partners. UTRGV and Texas A&M Kingsville supported the camera trapping and my work, and TxDOT funded the projects. We had a bunch of collaborators, graduate students, undergraduate students who sorted the, I don't know how many millions of photos, it was a lot, and provided help with processing and data collection and all of that. And I'll take any questions. Hopefully you have time. Yes.
I have one really simple question. Just there's a mammal you showed twice that I don't recognize on the bottom right there.
On the bottom right?
Yeah.
Yeah. So the question was about the mammal here on the bottom right. That is a baby feral hog.
Okay, so that's not the same. There's another picture earlier in the presentation of a long-tailed animal with a little bit of a white face.
That might have been a weasel?
Yeah.
Yeah, this one?
Yeah.
This is a long-tailed weasel.
Gotcha. Thank you.
Yes.
So I'm curious about the 1 year post-construction timeframe of monitoring
Yes.
and why that was selected, and then whether or not you might think that the level of anthropogenic use maybe affects the time it takes for animals to acclimate and choose that it's safe and it's okay to cross. I mean, we've seen a lot of that in camera traps. Like at first they're like, whoa, it's noisy, it's weird, it's dirt. But then eventually, right, things kind of come around and then they kind of acclimate to it.
Yeah.
So just curious your thoughts on those variables.
So the question was about why we only did 1 year post-construction and how anthropogenic characteristics might influence the amount of time to learn about those crossings and begin regularly using them. Part of the 1 year was because I needed to finish my dissertation. And the other part of that is some previous research has shown that there are differences in early on in the crossing's life and later on in the crossing's life. And I do think that the anthropogenic factor could be really important in determining how long it takes an animal to get used to a wildlife crossing. And I think that would be something that there is another PhD student who started after me to start working on these crossings. And I think that could be something really interesting that he could look at. I know he's still working on his proposal and stuff. But that long-term aspect and how the structural, environmental, anthropogenic characteristics, how their influence changes over time would be a really interesting thing to look at that we haven't had a chance to do that. But I think in the next few years, it's 2025, so the monitoring 5 years will end on the last road in 2027. So by that time, hopefully we'll have enough data to be able to look at some of that change over time. So maybe at the next ICOET, something we'll be presenting on.
All right, sounds good. Thank you.
You have time for one more?
Yes.
Yeah, I guess I want to reiterate that that it seems like, especially if there's focus on the ocelot, you really want to wait 5 years or so and see, because we know carnivores take longer to adapt. So anyway, from a conservation standpoint, that seems pretty huge.
Yeah. So the question was again about the amount of time in this study. And I think, well, yes, it definitely takes longer for a species like an ocelot or carnivores in general to get used to wildlife crossings. Some of our crossings, especially those ones that were in that big clump that were very diverse, those are our crossings that we're getting ocelots at, that we have gotten them. And while for some of those crossings, ocelots never actually used that crossing, the fact that they're coming to those sites, and maybe eventually if we actually get a resident ocelot in the area, they might actually start using that site. And that would be the site that they would use. And those are our sites that we're predicting would have the greatest species diversity. So from that perspective, even after only 1 year, we are seeing that these diverse sites are the ones that are also getting ocelots.
Thank you very much.